So in this next half of the intro to limits notes, we kind of jump in where we left off. The last thing we were talking about is how you can basically just directly substitute something as a first attempt, and that is always, always the first attempt that you should make. So if it looks like something can just get subbed right in, do it. Sometimes functions do exactly what they're supposed to do. Sometimes there are no holes, sometimes there are no asymptotes, sometimes they look like they're going to hit a y value, and they do hit that y value. And that's most of the time, actually. It's pretty rare and weird that a function would end up having a hole. So starting with polynomial and rational functions. Polynomial functions, you're not going to see holes. You're not going to see asymptotes. These are like your parabolas, your lines, your cubic functions. There's nothing unusual about those. So this first theorem that we are going to look at, part 1 of theorem 2, if you want to take the limit of f of x as x approaches c. So this form right here, this is like a very, very generic form for a polynomial. So each a, like an minus 1, all the way down to a naught, that represents a constant. And then x to the n minus 1. So this could be something like 4x to the 5th plus 7x to the 4th, and then it would go all the way down to just a constant with no variable attached. So like I said, just a very generic way to write a polynomial. So the limit is basically just exactly what you would get if you were to plug the c right in for x. So you'd have the first constant and then times c to the n instead of x, you would plug in the c, and then plus the next constant times c to the n minus 1, and then on and on and on, all the way down until you hit your last constant. Okay, so all you're doing there, and this works for every single polynomial. If you're trying to find the limit of a polynomial, as x approaches c, whatever c is, you just plug it right in. That's it. Polynomials don't do anything weird. Okay, next one, part 2, talking about rational functions. Rational functions usually don't do anything weird unless the denominator is 0. Okay, so if you've got some sort of quotient, like f of x over g of x, and you're trying to take the limit as x approaches c, basically what you're going to get is just plugging in c, unless g of c is equal to 0. If it is equal to 0, then we have to get a little bit more complicated. So this part of the theorem basically says, as long as plugging in c does not give you a denominator of 0, go right ahead and plug it in. Direct substitution is the easy way. Okay, so a couple of theorems that we can work with here. So for example 4, let's use those theorems. Here's a polynomial. Looks a little bit different than this, just because it's in kind of factored form, but if we're looking for the limit as x approaches 3, all we have to do is plug 3 in. The function doesn't do anything weird. As x approaches 3, it's going to do exactly what it's supposed to. And what it's supposed to do is get whatever y value we get when we plug in 3. Okay, so our order of operations says we subtract 2 minus 3 first. That gives us a negative 1 times 3 squared. That would give us a negative 9. So again, if we were looking at this graph, it would look like the y value is approaching negative 9. It actually is. That is the limit. It's as simple as that when you're dealing with polynomials. Okay? Next one is a rational function. Remember this phrase. This phrase is very important, provided plugging in c does not give you 0. So look at your denominator first. The value they want is 2. If you plug in 2, it does not give you 0. So that means we've got the go-ahead. We've got the green flag for direct substitution. So just plug that 2 right in. Okay, we're just going to simplify everything up. So 2 squared is 4, plus another 4, plus 4 is 12, and then 2 plus 2 is also 4, and of course that reduces down to 3. So as x approaches a value of 2, that means my function is approaching a value of 3. And again, you could look at those graphs. There's no holes, there's nothing funny, it's just doing exactly what you'd think it's going to do as x approaches those values. Okay? Next, we can kind of expand that method for trig functions, log and exponential functions, and then composites of functions, like plugging one function into another function. Sometimes it works. Sometimes all is well. Sometimes it doesn't. And this is basically your only indication as to when it wouldn't go well. Anytime you'd have a denominator of 0. So like with trig functions, for instance, it's possible that you could have a denominator of 0. With logarithmic functions, especially if you've got some sort of ratio of functions, it's definitely possible that direct substitution may not work. So if direct substitution doesn't work, then we do what we call algebraic manipulation. We've got to do either some factoring, some rewriting, something of that nature, so we could write it in a slightly different form. Okay, so this function right here, x squared minus 1 over x minus 1. We always attempt the direct substitution first. Try it. If you try to plug in the 1, it does give you a denominator of 0, which means we can't use the theorem that we have up above. So we go to our next method, which is algebraic manipulation. And so factoring. Factoring is the number one way to manipulate algebraically. So when you're writing this, you always, always, always have to keep writing the limit clause right here, because this function isn't equal to a manipulated function, but their limits are equal. So you write this each and every time. So in the numerator, this factors down, and this function should look familiar. We just dealt with it in the previous lesson. And then my denominator is x minus 1. So when I cancel this, again, it's not that this function is equal to this function. What's important is that their limits are equal. Okay, so that's why you have to write this, the limit clause, every single time. Okay, so once you've manipulated it, then you can try direct substitution again. So direct substitution didn't work here. But if I try to plug in the 1 now, it'll work. I just plug in 1 for the x plus 1, and I get 2. Okay, so a little bit of algebraic manipulation ended up giving me exactly what I had a couple pages ago. See how for this function, I found a limit of 2. That was kind of the graphical way. I just did it algebraically right here, and I got the same answer. Okay, this one's a little bit different. This one you don't really factor. This one you do somewhat of a rewrite. So limit as x approaches 0, and then tangent. Anytime you have trig, if you guys remember doing those wonderful trig identities at the end of pre-calc, you learned that if you're trying to rewrite something, you should probably write it in terms of sine and cosine. Okay, so let's start with this. Write tangent as sine over cosine. Then that's the numerator, and then that's all over x. Okay, so this one, the manipulation is a little bit more out there. Okay, so we're going to do this. Limit as x approaches 0. And then this is sine x over cosine x, and then times. So instead of dividing by x, we're going to multiply by 1 over x. So this is kind of the whole inside of the function that we have right now. So it still isn't really looking like anything that's going to help. So I want to remind you this. You guys remember this function that we saw at the beginning of the last set of notes? We know this. We know the limit as x approaches 0 of sine x over x is 1. We can work with that. Okay, so flip back. So I'm going to take this. All I'm going to do is I'm going to swap the numerators. It's a perfectly legitimate move. Just a lot of manipulating. So I'm just going to do a little numerator swap here. Okay, so if I multiplied it all back out, these two things would be exactly the same. But this limit is something I know. Okay, so remember one of my properties that tells me if I have two separate functions multiplied together, I just take the limits separately and I multiply those limits together. So that is what I'm doing right here. I'm going to take the limit of the first one and I'm going to multiply it by the limit of the second one. Okay, so this one right here is an answer I already know. I just pointed it out on the previous page. This is 1 times, and then this, I don't need anything fancy. I can actually just plug it right in. Because if I try to plug in a 0, cosine of 0 is 1. So direct substitution works for this one. So 1 times 1, of course, is 1. Okay, so a little bit fancier of manipulation that we had for that one. But we still end up kind of with the same results, manipulating until you get to a point where you can use direct substitution. This, by the way, is something that you're eventually going to have memorized. All right, AP problem. This requires a little bit of manipulation. Notice if I tried to plug in a 0, I would get 0 plus 0 over 0 plus 0, which is indeterminate. But if I do a little factoring, I can get something to cancel. So notice how every single one of these has at least an x cubed. So I can factor and cancel an x cubed. So this is a sample of a multiple choice question off of the AP test. You'll have 45 of these. So see this, I can factor out an x cubed, and I'll have 2x cubed plus just a 6. And then here I can also factor out an x cubed. So I'll have a 4x squared, and then here there would just be a 3. So remember why I told you have to keep writing the limit clause over and over again, because these will cancel, but it doesn't mean that this function is equal to this function. It means their limits are equal. Okay, so now this new and improved function, I can go ahead and plug the 0 in. Because if I plug in the 0, I get 6 over 3, which is 2. Okay, so that's one of my options. So the good thing about the multiple choice section of the test is you don't have to show any work if you don't want to. So if you were able to kind of do that in your head and save time, totally fine. Not a good habit to get into. I don't want you to get into the habit of not showing work, but we'll talk more as the AP test approaches about what's necessary to show and what's not. Okay, let's finish this up. Couple quick things. Okay, so example 6 tells us to use a graph. Okay, so that's, I literally mean just as simple as opening up a graph. So you can open up a new document or just add a page to your document. You're going to add graphs. If you're on an 84, just type the y equals in the upper left corner and you can type this in. Notice the calculators do have kind of like a fraction button. If you look above the division key, you can hit Control and then hit the division key and it opens up a separate numerator and denominator. It keeps things simple so you don't have to deal with a lot of parentheses. Okay, so x, and then your power key is over here, the little caret key. You can type in the third power, -1, and then over x minus 2. Okay, so there's our graph. Okay, and this is actually kind of a weird example because there's another piece of the graph that we don't see. So I want to show you, hit menu, zoom out. We're going to take option 4. And we are going to zoom out around where x equals 2 would be. Okay, we're going to do it one more time. There it is. Okay, so it is like hiding way up there. You've got this little piece right there. So we're just going to do a really, really quick general sketch. So you've got this piece that kind of comes down like this and then goes like that. And then way up here we've got this little piece like that. Okay, so just a really, 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 really general sketch. Okay, so now notice, x minus 2. If I try to plug in the 2, I get a 0 in the denominator. The reason I get a 0 in the denominator is because I have what we call a vertical asymptote. If the denominator is 0, you can either have an asymptote or a hole. Okay, and we'll explain in this next little section when you would know when you're getting a 0, or I'm sorry, when you're getting a hole and when you're getting an asymptote. So here you have an asymptote. This graph really explains why the limit doesn't exist, because the limit says as x approaches a certain value, what does y approach? Okay, so let's look over here. As I come in from the left-hand side, I'm getting closer and closer to that dotted line. Y values are just going lower and lower and lower and lower. As I approach from the right, my y values are just growing. They're not approaching the same thing. That's a problem. Okay, so the reason that it doesn't exist is because it never approaches anything. My values are either getting bigger and bigger and bigger or smaller and smaller and smaller without consistently approaching something like they did on the previous page. Okay, so the reason that my limit doesn't exist is because I have a vertical asymptote. So what we would write is we would say the limit of f of x, or whatever the function is, as x approaches 2, just a very simple abbreviation, does not exist. Okay, so having a vertical asymptote, these are something that we call infinite limits, meaning that the y value isn't actually approaching anything, it's getting infinite, either infinitely large or infinitely small in the negative direction. Okay, so this is our really, really informal method. I am I'm not kidding about quite how informal this is. Okay, so the informal method that we are going to use. Start with this, two different limits. We can take the limit as we approach 2 from the left. I think you guys may have seen this notation before. We can also take the limit as x approaches 2 from the right. So this is what I'm talking about as we come in from the left. This is what I'm talking about as we come in from the right. Okay, so what we do is we see what happens when we plug the 2 in. So plugging in 2 from the left means something really close to it, but on the left, like 1.9, 1.999. So try to plug in the 2 into the numerator. 2 cubed minus 1 over, and then if I plug in 2 down here, 2 minus 2 is 0. That's bad. I can't have 0 in the denominator. So here's what we're going to write. 2 minus 2 is really, really close to 0 if x gets really, really close to 2. If we're coming in from the left, that means we've got something like 1.99999. If I plug that in, something like 1.99999 minus 2 is a very tiny number, but more importantly, it is a negative tiny number. It's not going to be positive, it's going to be a negative tiny number. So my numerator, 2 cubed minus 1 is 7 over a negative tiny number. Let me show you what that looks like. If you have something like 7 and you divide it by a negative teeny tiny number, you get a negative gigantic number. The smaller the denominator, the bigger this number gets. So we say negative infinity, which is exactly what's happening here. As I come in from the left, my function is plummeting down towards negative infinity. Okay, and I can do that same informal method here. If I try to plug in 2, there is no problem plugging 2 into the numerator. But there is a problem plugging 2 into the denominator, because I would get 0. However, I am specifically coming in from the right, which means values like 2.0001. And if I plug in 2.0001 minus 2, I get a tiny number, but again, not just any tiny number, I would get a positive tiny number. Okay, so the number 7, which is positive, over a positive tiny number would give me a positive very large number, which again is exactly what's happening right here. So this is a little tricky. We will talk about this when we're all together, but it's a very informal method that you can use just to gauge what you think the infinite limits are going to be, whether it's negative infinity or positive infinity. Okay, last little thing here, talking about our one-sided and two-sided limits, which I just introduced here, but we're going to make them a little more formalized. Okay, so different limits from the left and from the right, which is just what we had here. So our first notation, the limit of f of x as x approaches c, and then notice we have that little superscript of a negative sign. Okay, that is the limit as x approaches c from the left. Okay, and then my second very similar notation, I put a little superscript plus right there, just like I did up above. And this is the limit as x approaches c from the right. Okay, so we're going to analyze this graph right here. Going to take tons and tons of different limits. So let's talk about what happens at, let's see, 3. 3 would be a good one. Okay, so the limit as x approaches, or I'm sorry, negative 3. As we approach negative 3 from the left, coming in, approaching, it looks like my y value is going to hit negative 1. The fact that I have a hole does not matter. Okay, so I'm approaching negative 1. As I come in from the right, it's also approaching negative 1. Okay, so as I approach negative 3 from the right, coming closer and closer and closer to this x value of negative 3, my y value gets closer and closer to negative 1. Okay, again, it does not matter that there's a hole here. The function value is positive 1, but the limit is negative 1. So from these two, I can say that the limit exists. Okay, so limit, negative 3. the limit is 1. The left hand goes to the same value as the right hand side, and so we say that the limit exists. Okay? Let's look at -1. The limit of this function as x approaches -1 from the left. So here's -1. I want to approach from the left. As far as I can tell, my y value is getting closer and closer and closer to 1. So we say 1. Then I check from the right-hand side. So -1 from the right. As I approach this value from the right, as far as I can tell, my y value is approaching 2. It's just 2 the whole time. Okay, so here, the left hand approaches 1, the right hand approaches 2. So if I asked you for the limit in general, it doesn't exist. It's approaching one thing from the left, but something different from the right, so you say the limit doesn't exist. Okay, let's see 1. Okay, from the left, as I approach from the left-hand side here, the y value is just consistently staying at 2. Okay, now let's approach 1 from the right. So I'm approaching this x value of 1 from the right, and it looks like my y value is getting closer and closer to 0. So this one we actually have something pretty weird going on. The left-hand limit is 2. The right-hand limit is 0. The function value is -1. Okay, so this one, we would say that the limit does not exist. Now, this weird point has nothing to do with why the limit doesn't exist. The limit doesn't exist because these two don't match up. This has nothing to do with it. Okay, so we saw a couple different scenarios there. Now, we could play this game at every single one of these x values, but I think these are a solid couple of examples here. So, to sum up this right here, we are going to write down a theorem. We can say that a function f of x has a limit as x approaches c, any x value, if and only if. We're going to do it in words first, then in symbols. The left hand and right hand limits at x approaches c exist and are equal. And so in symbols we say the limit of f of x as x approaches c equals L. We usually just use a capital L for a generic limit. And then these double arrows mean if and only if. Like this is true if this is true, and this is true if this is true. We say the limit as, x approaches c from the left, that should be an x, not a c, equals L, and the limit of f of x as x approaches c from the right equals L. So saying that they exist, because it's possible for a limit to not exist at all, and that's something that we'll get into as we get further into the chapter. So they're both equal to L, which means they both exist, but again, they're both equal to L, which means they're equal to each other. So we say a general limit exists as long as the left and right hand limits exist and are equal to each other. All right, so that is it for our intro to limits.